In this video, I'm going to be talking about resistors in series and parallel. Unlike a previous video I did, I'm going to be doing this with calculations, so that's why I call it quantitative analysis. It's part of topic 5.2 of the IB Physics Syllabus, so it is relevant to both SL and HL syllabus. Take a moment and read the success criteria of what I plan to cover in this video. Okay, so when we do some calculations with circuits, in addition to Ohm's law, there are two other things we use a lot, which are Kirchhoff's circuits laws. Now, when at first they seem like additional material we need to cover, really they just boil down to the conservation of charge and the conservation of energy. This is what they look like in the data booklet. So let me just go through and talk about these first before we start using them. In this case, it says the sum of the voltage or potential difference equals 0 in a loop. Well, I have another way of thinking about this. I like to say the total potential increase equals the total potential decrease. In other words, if I have 5 positive, then I have 5 negative, and I add them together, I get 0. So what do I mean by total potential increase? Well, if I look at my circuit here, I have a cell. So that is going to add potential energy to my electrons, electric potential energy that is. And as it goes through my circuit, when it goes here to the resistor, that electric potential is going to be then changed into heat energy or light energy or something in my load. In other words, the electric potential energy of the electrons are going to decrease and they're going to come back to the beginning. Now, this is potential energy, and one of the things we have to worry about that is always what is the reference point. So just because I'm saying it comes back here and it's at the beginning again doesn't necessarily mean it's 0. It just means whatever potential increase that I've given it in the cell, it has decreased here. So really, what am I going through with this? I'm increasing electric potential energy and I'm transforming it to something else and back. So this is actually the same as saying a conservation of energy. So let's look at the second part. It means the sum of all the current equals 0 at a junction. Here's another way of thinking about that. The total current going into a junction equals the total current going out of a junction. So if I look right here, if I have 5 amperes of current coming in, I'm going to have 5 amperes of current coming out. Well, all that's meaning is, remember, current is the amount of charge per time going past a point. So it's related to the number of electrons moving past a point. And so let me put it in another words. If I have 10 electrons coming in here, I better have 10 electrons coming out. If not, I have poof Harry Potter magic going on, and that would violate the conservation of matter, or more specifically here, the conservation of charge. Okay, so let's start to apply Kirchhoff's voltage and current laws to resistors. So in my diagram here, I have 2 light bulbs. The important thing is that it's going to be something that we call a load that's going to be using up the potential difference. Filament lamps aren't actually ohmic resistors, which means the resistance is constant, but they do well for my illustration. So let's think about Ohm's law then. We have R equals V over I. If I move that around, I get V equals I R. We're going to need that in a little bit later. So we just talked about Kirchhoff's voltage law. Let's use that, because in this example I have one place here where I have a potential increase, and I have 2 places where I'm going to have a potential decrease. Let me call this one here R1 and this one R2. So let's use Kirchhoff's voltage law. The total voltage, that's the voltage that's at my cell, is going to equal the potential difference in our first resistor and the potential difference in the second. That means that my total potential increase equals my total potential decrease as I go through the circuit. Now let me put in that Ohm's law. It's going to tell me then that the total voltage is also the total current and the total resistance. At V1, I will have the current in and V2. And remember, Ohm's law, either you're talking about each single component or you're talking about the total amount in the circuit. And it works in both ways. But there is one last thing we need to think about with being in series, and that is that the current that leaves here, let's use Kirchhoff's current law. All the current that leaves here has to come to here, which means it has to come to here and so forth, which means that the current in all the places in a circuit in series is going to be exactly the same. So that means I can cancel it out. So this leaves me with the total resistance in my series circuit is R1 plus R2. Now I want you to remember this is only for series circuits, and that's because in order to cancel out that current, I had to have the current everywhere in my circuit. That's only true for series and not for parallel. We sometimes call this total resistance, or sometimes we call it effective resistance. If it's part of a bigger circuit and we want to know what is the combined resistance of any two parts, we'll call it the effective resistance. And here's what it looks like in our data booklet. But, and this is a big but, it doesn't tell you whether this is series or parallel. That part you need to remember on your own. Okay, so let's move on and do it in parallel. I've got another circuit here, and you can see now I've got both things, and I've got two different branches, which means now I have things in parallel. Again, let's call this one R1, and this one called R2. So let's think about what's going to happen with our voltage law. If I have a potential increase here, and my electrons go around, and they go through here and back, my total potential increase, it only has one place on this circuit that's going to actually use it. So that means that in this case, I'm going to have my V total will equal V1, or likewise, it will also equal V2, because it's a different set of electrons that are going to go in this direction. So that brings us up to using Kirchhoff's current law. So let's think about this. Whatever current leaves here, now I've got a junction. I've got some going to resistor 1, and some of it will go to resistor 2. So in terms of math, I have I total will equal the current into number 1, and the rest of the current will go to number 2. Now, if we have R1 and R2 being exactly the same resistance, then those two currents will be split evenly. Now into the second equation, I'm going to substitute Ohm's law. Right at the top, R equals V over I, and let's isolate that for I is going to be V over R. Take a second if that was too fast for you. But now what I'm going to do is I'm going to substitute that into Kirchhoff's current law down here because it's the one that has the addition. So the total current is going to be the total voltage divided by the total resistance. That will equal V1 over R1 and V2 over R2. Again, because the voltage is going to be the same in both these branches, I can now do some canceling because the voltage is going to be all the same. What does that leave me with? 1 over RT equals 1 over R1 plus 1 over R2. And here's one of the things I really want to point out. This is not the same as in series. You cannot take this equation here and then just say, oh, that's the same as RT equals R1, R2. I'll just flip them all individually. These are fractions, and what that means is you would actually have to have a common denominator and put them together and then invert them. It's not the same. In our data booklet, we'll have this one. And so you just need to remember that the odd-looking one is resistors in parallel. When we get to topic 12, it's going to look very similar when we talk about capacitors, but they're in the opposite way. Don't worry, if you're an SL, you'll not have to do it. So let's go through a couple different examples. So here we go. I've got a circuit, and you can see I was talking earlier about the idea of using effective resistance. If I wanted to use S and R, and I wanted to know how much resistance they have since they are in parallel, I could use, instead of RT, I'll just call it the effective resistance of these two things in parallel, and then I would add it to this one here, which is in series with it, if I wanted to get the overall effectiveness of this circuit. So, what must be known in order to determine the value of I? So you might say we need to use Ohm's law. Well, I don't actually think we need to do that complicated. There's something else that we could use to determine the value of this current, and that is Kirchhoff's current law. You see here I've got 4 amps of current, so that right here I have that 3 amps has come out here. That means I'm going to end up having 1 amp of current right here. So how much would I have right here? Right, it's back to 4 amps. One more thing I want to point out in this question is if there has more current here than this side, what does that mean about the resistance of S compared to the resistance of R? Hopefully you said that S must have a smaller resistance because it has a greater current. I like to think of it as people running a race. If I asked people, all these people to start, would you like to run a 100-meter sprint or would you like to run a 2-mile sprint? Which way would you go? Well, there's always a couple people that would say, I'll do the longer distance. Why? Because I get out of class more. It doesn't mean it's going to be 0 people choose the longer distance. So just to sum up, what must be known in order to determine the value of I? I just need to use Kirchhoff's current law. I actually don't need any additional information. Okay, here's another one. When deriving a formula for the combined resistance of 3 different resistors, Kirchhoff's laws are used. Which physics principle is involved in this derivation? Now I'll go through each of the answers. Well, let's come back to A, because if you were listening earlier, you know A is going to be the answer. So let's talk about the other ones. Okay, so B, the direction of flow of charges from negative to positive, true. But this isn't actually a principle we're using to calculate the combined resistance. The next one, the potential across each resistor is the same. Well, let's go back and double check. It says it's in series. So the problem with that answer is that the potential difference isn't going to be the same. That would be true for if it was in parallel. In series, it sometimes will occur, but that's only if the resistance of both pieces are the same, but we still wouldn't be using that to calculate the combined resistance. Now for the last part, the current varies in each resistor. And again, I tell you to go back and look at the question. It says it's in series. So the problem there is, in series, we always have the currents the same. Okay, so let me just put the equations we have for our series and parallel resistors. Now, series means RT equals R1 plus R2. And one of the big important things here is RT is always going to be bigger than R1 or R2. And one of the other things that happens with this one in parallel is RT is actually always going to be lower than R1 or R2. So let me just do a quick example. Let's say R1 is 6 and R2 is 12. So if they were in series, then RT would equal 18. It is bigger than either of the other two. If I have them in parallel, then 1 over RT is going to be 1 over 6 plus 1 over 12. 1 over RT will then be 3 over 12. RT equals 4. And 4 is smaller than either R1 or R2. Okay, so what does that mean for our question up above? Well, in this combination, since all 3 of them are in parallel, then what that means is that it's going to have the smallest effective resistor. So if I go back to my answer here, I'm going to get rid of these two. It also means that since this one has one in series, then the two in parallel, it's going to have a higher resistance than this one that has them all combined. And that would make my answer D. Okay, so in this question, each of the resistors has a resistance of 2 ohms. Which arrangement gives the largest reading of the ammeter when the same potential difference is applied? So first of all, we would normally be thinking about using Ohm's law. If I move that around, current is going to be voltage over resistance. And so if I want the largest current, since we have the voltage or potential difference being exactly the same, I would be looking for the smallest resistance. So let's take a quick look here. Well, that's not going to be this one, because we can see that they are in series, so it's going to have the largest effective resistance. So that one's definitely out. In B, I have these two in parallel and then the ammeter right after it. That's going to have a lower resistance than 2 in series. Let's look at the difference here. I'm actually going to look at the current in just one of the branches. Well, that means it's going to be lower than here, because if we have Kirchhoff's current law, we have these two currents going to be adding in to give this current here. So then we know definitely that one's out. So then let's take a look at D. D has something a little unique. It has this ammeter in between, and we have them at the junction. So here's one of the things you need to remember about ideal ammeters. Ideal ammeters have very low resistance. I have another video on the differences between real and ideal ammeters and voltmeters that you might want to watch. Okay, so what does that effectively do? Well, really what you've got is a short circuit. So remember I said that when we have things in parallel, the most current is going to go to the one part that has the least amount of resistance. So this is going to get even more than we get in these two conditions. So in this case, the answer is D. Okay, an electrical circuit is shown with loop X and junction Y. What is the correct expression of Kirchhoff's circuit laws for loop X and junction Y? Well, let's do the current law first, because I find it the easiest. So whatever current we have coming in here into junction Y is then going to equal coming out in these two directions. So that means I1 is going to have to equal I2 plus I3. If I look down below, this one's wrong, so is this one. So my answer is going to have to be A or C. Okay, so now let's talk about the voltage law. Remember, the total potential increase will equal the total potential decrease. So the amount of increase will be here, E. And where is it going to go? It's going to go sum to this first part, and then let's take a look. It talks about number 3. It's going to talk about going down to this branch and coming back. So all of the energy given here is going to have to go to V1 and V3. So let's look what we have down the bottom. In this case, it has V1 minus V3. No, that's not going to be true. So it's going to come here. Now you might say, well, where's this negative coming from? Well, it's trying to say that if these two were using energy, this one is not using energy, it's gaining energy. In this case, my answer is going to be A. Okay, so that brings us to the end of this video. One last thing I want to point out is that in the IB, the combination of resistors is perhaps a little bit easier than some exam boards out there. We will typically not have more than 2 resistors in parallel, or a combination of 3 things. So I've seen some pretty crazy circuits out there. They don't actually get that complex. Many of the ones, remember, if they're in multiple choice, you're going to have to be able to calculate them without a calculator. So they're going to have to be easier sets of numbers. And if they are on paper too, the structured response questions, then there'll be maybe some not nice numbers, but we're looking for the concepts rather than trying to trick you on some of the values. I hope this has helped you, and reading through the success criteria, now you'll be able to use Kirchhoff's laws.